So, we are going to look at few definitions now. The first one on the list is solid angle. Okay. So, typically in normal geometry that you have done so far, so supposing if you have a two-dimensional system, and if this is theta and this is r, you know what is going to be the length of that arc, right? What is the length of the arc? R theta, right? R theta is the length of the arc. Now, if we want to know, so this theta, the meaning of this angle is what is the angle that is subtended by this arc to that particular point in the center, right? So, if I draw a circle, if I had complete this circle, this angle tells you what is the angle that this arc subtends to the center of that particular circle. Now, we need to extend this. So, this is very good in a two-dimensional polar coordinates. So, this definition is for two-dimensional system in polar coordinates. Now, we need to extend this to a three-dimensional system. So, note that radiation is a three-dimensional process. So, you need to extend this concept of the angle subtended by a given surface. So, here it is the angle subtended by this arc, which is a one-dimensional system. Arc is a one-dimensional system. So, what is the angle that is subtended by this one-dimensional system to the center of that circle? So, we need to define what is the angle subtended by a surface. We need to define what is the angle that is subtended by a given surface to a particular point. Okay. So, supposing here is a point object, okay. By the way, this angle is what is called as solid angle, and the symbol that is given is omega. Omega is the symbol that is given for solid angle. So, supposing if there is an object here, okay, and you have a surface, this is a surface, okay. So, if I call the object as, let us say dA1 is the surface area of that object, and the vector points in the normal direction to that surface. So, note that surface area can actually be quantified as a vector. So, it is a vector which is pointing in the normal direction, and let us say this is A2, surface A2, and this is the vector. So, depending upon the direction, you can say it is pointing inwards or outside. So, the question is, what is the angle that is subtended by this surface A2 onto that point object? So, that is what we need to find. Okay. So, the solid angle is, so that is the solid angle. So, if I call this as d omega, okay, so I can extend this concept of finding the angle in two dimensions into a three-dimensional system. Okay. And the way I do that is, if supposing the linear distance between the center of these two is r, okay. So, d omega is essentially defined as dA2 by r square. Okay. So, this is the definition of solid angle. Okay. This is the area of the object divided by the distance between the center of the object. Is that clear to everyone? We are going to now find out how to find this solid angle for any arbitrary three-dimensional system. So, supposing I now define, this is my y direction, this is x, and this is, let us say, z direction. Okay. Now, I can draw a hemisphere. So, I can draw a section of the hemisphere. Okay, so this is the section of the hemisphere. Okay, so let us assume that there is a hemisphere which is present in 3 dimensions, and if I assume that, okay, so this is the angle, if I call this as d phi, so this is the angle that is actually subtended by this particular area on the xzy plane, okay. So d phi is the angle of the projection on the zy plane, okay. So d phi is the angle of the projection on the zy plane, and if I call this angle as theta, okay, so that's the angle of the line that joins the center of these two objects with the x axis, okay. So that's angle theta. So I have now clearly defined two coordinate systems. So this is my theta and this is my phi. Phi is the angle that actually comes out of the board, and theta is the angle which actually goes in the xy plane, okay. Now I can define this small angle here, this is d theta, this is the differential angle that is subtended in the xy plane of that surface, okay. So keep in mind that there are two different angles in two different planes. So d theta is the angle that is subtended by this particular surface if you project it on the x and y plane, okay. So the objective now is to find the area dA2 in terms of these angles. That's what we need to do, okay. So supposing I call this length as L1 and this length as L2, so that's the linear length scale of the two sides. So dA2 is nothing but L1 into L2. So if I know what L1 and L2 are, I am done. I can find the solid angle. Okay. What is L1? How do I find L1? From d phi. How do I find L1 from d phi? Okay, so I'll help you. So supposing, so this angle is d phi. What is this side? What is that distance? So this is r. What is this distance? R sin theta, okay. So L1 is r sin theta, and what is L2? Oops, sorry. L1 is r sin theta d phi. So this length is r sin theta, and therefore L1 is r sin theta d phi. What is L2? Whatever, it doesn't matter, it's a differential element. Whatever is the length of the arc, it's not a linear line, it's an arc, so it doesn't matter. All I am saying is what is the length of that arc, that we should be able to find. It doesn't matter whatever is the shape of the object. So all I am saying is it's just a differential element. Now if you integrate it over the whole surface, whatever surface you have, you should be able to make it. What is L2? R. So note that this angle is d theta, and so the projection is this cone here. So you see this triangle, that's the projection, right? So L2 is nothing but r d theta. So this is the radius, and the angle between them is d theta. So the length of the arc L2 is r d theta, and therefore the area is given by r square sin theta d theta d phi. Okay. So from here I can read out that d omega, which is the solid angle which is subtended by that differential surface on dA1, is given by dA2 by r square, which is sin theta d theta d phi. Is that clear to everyone? You must understand this very clearly. Okay, supposing if I want to find the solid angle of the hemisphere, how do I do this? Solid angle of hemisphere. I want to find the solid angle of hemisphere. How do I find the solid angle of hemisphere? Yeah? 180 degree? No. Theta goes from 0 to pi by 2, that's right. And then note that there are two angles. Hemisphere is a three-dimensional object. So it is defined by two angles. So omega of a hemisphere is given by integral 0 to 2 pi on phi. So phi, note that phi goes all the way around in zy plane. So, and this will be 0 to pi by 2 sin theta d theta d phi. That's it. What's this integral? Not hard. 2 pi integral 0 to pi by 2 sin theta d theta. What is that? Integral 0 to pi by 2 sin theta d theta. Come on, folks. 1. Not that hard. Minus cos pi by 2 plus cos 0, that's equal to 2 pi. So the solid angle that is subtended by a hemisphere is 2 pi, not 180. And what will be that for a sphere? It will be 4 pi. So the units that is used here is called steradians, and it's typically represented as SR. So that's the unit for solid angle. It's called steradians. Okay. Any questions on this so far? You must understand this geometry. So we will be using, I'll not be drawing this picture again and again, but you must clearly understand how this geometry is constructed and how we find the surface area of the, how we find the area of this arbitrary surface, and how we are able to calculate the solid angle. So the whole concept of quantification of radiation, it hinges upon this picture. The ability to calculate the solid angle is very, very important when you are doing any radiation calculation. And all through the radiation topic that we will see, I will not use the word solid angle, but the solid angle is actually inbuilt in some of the expressions that I am going to derive shortly in today's and the next lecture. So this sin theta d theta d phi is something that you will see that it will appear in almost all the expressions that you will see for radiation. So it's very, very important to understand how you get the solid angle. Any questions on this? Okay. So L1 is essentially the length of this arc. Okay. L2 is the length of this arc, right? So this is a differential element of arbitrary surface. So L1 is nothing but this length multiplied by d phi, and this length is r into sin theta. So this is a theta, and so sin will be the opposite by hypotenuse is sin theta. And so the length of this particular, linear distance is r sin theta multiplied by d phi will give you L1, and this length is in the xy plane, and so that is radius multiplied by the angle in that plane, which is d theta. So r d theta will be L2 and r sin theta d phi will be L1. Any other questions? Okay. Yes. It's a projection. So it doesn't matter where you write the projection. I've just, for convenience sake, I've written it here. It doesn't matter. The angle remains the same wherever you write the projection, whichever plane you write the projection, whichever x whichever x value you write the zy projection, the angle remains the same. It's just that the length will be different. So if I write my projection here, okay, I can always do that, right? I can always do that. So this distance is actually equal to this distance on the projection. I have just represented this projection so that it is easy to understand that the length of the arc is L r sin theta d phi. So all I have done is I have just taken this projection and represented it here, that's all. No, it's not. We'll see that. So obviously the distance at which the object is placed is going to make a difference. We will see that. In some of the definitions we will see. Any other questions? Okay. Alright. So we're going to move to the next definition. So we are going to define a quantity called radiation intensity. It's the radiation intensity, and the typical symbol that is used is I, okay, and a subscript lambda means that radiation intensity at a particular wavelength lambda, and that's going to be a function of lambda, theta and phi, okay. So it's going to be a spectral property, so it's going to be dependent on which lambda, it's going to be dependent on what angle in theta direction and what angle in phi direction, okay. So it's defined as the intensity of radiation I can also put a E here which stands for emission. So give me a second. Intensity of radiation emitted by a surface at a certain wavelength lambda per unit area of the emitting surface per unit area of the emitting surface, okay, per solid angle subtended by the receiving object on the emitting surface per unit wavelength lambda. So that's the definition of radiation intensity. So intensity of radiation emitted by a surface at a certain wavelength lambda per unit area of the emitting surface, if dA1 is the emitting surface, per unit area of the emitting surface per solid angle that is subtended by the receiving object. So note that the intensity now depends upon both the receiving object, what is the amount of intensity that is emitted by the surface on that direction. So it has to obviously be a function of the receiving object, its area and the solid angle per unit wavelength d lambda about that particular wavelength. So this is the definition of the radiation intensity, and so what we are going to see is how to define heat transfer rate based on the, so when we translate this definition into a mathematical form, lambda comma theta comma phi, okay, so that will be given by dq, which is the differential amount of heat transport rate, the rate at which the heat is being emitted by that surface, divided by dA1, okay, so that tells you the flux, divided by the solid angle d omega divided by d lambda. If this is my surface which is emitting radiation, okay, now it matters where it is being placed. where the receiving object is being placed, because the doesn't matter, even if you keep the distance constant, okay. So supposing if you have a concave surface, okay, whatever is emitted by the concave surface is not received by itself, okay. Whatever is emitted by the concave surface, they always leave and go out of the concave surface. Now supposing if I have a convex surface, okay, supposing if I have a convex surface, then whatever is emitted by this object in this location is now going to be intercepted by the same object. So the orientation plays a role. So for example, see here, supposing I take this surface here, it is emitting radiation in all directions, right? So the radiation that is emitted is going to be intercepted by an object which is placed here. The radiation which is emitted here is going to be intercepted by an object placed here. There is no reason why I should assume that all the radiation is constant in all directions. So it does matter where the object is placed, even though the distance between the object is the same, it does matter where it is placed. Any other question? Okay. So now dq by d lambda, okay. So this is so this is called as, generally the terminology that is used in your textbook is dq lambda, which is basically the heat transfer rate per unit wavelength, and so that's given by I lambda E lambda theta comma d phi multiplied by dA1 into d omega. Okay. What is dA1? What is the area? So keep in mind that, maybe I'll draw the picture again. So this is the area vector of that object, and if this is cos theta, this is theta, then the area that is actually in the direction of the receiving object is dA1 into cos theta, right? So that's the area vector which is pointing in the direction of the receiver is dA1 into cos theta, okay. And what is the solid angle? dA1 by dA2 by r square. So note that the solid angle depends upon the area of the receiver, not the one that is emitting. So keep in mind that if this is A2, if let's say that dA2 is the area of the receiving surface, then d omega is defined by dA2 by r square. So this is the area component in the direction of the line that joins the center of these two objects, and so d omega is dA2 by r square, and that is given by sin theta d theta d phi. So that's the solid angle that is subtended by this surface on the emitting surface dA1, okay. So if I put that, it will be I lambda E phi cos theta sin theta d theta d phi dA1. So that's the heat transfer rate per unit wavelength, okay. So I can define flux dq lambda. So note that double prime when I use, it's flux, okay. So that will be dq lambda by dA1, which is the flux at which the emission is occurring from that surface. So that will be I lambda E lambda comma theta comma phi sin theta cos theta d theta d phi. Okay, so that's the definition of flux of radiation from emitted by a given surface. So I would encourage all of you to actually go over this before you come to the next class. You must completely understand how this expression is derived. So everything that we discuss in radiation completely hinges upon how this expression is derived and how the three-dimensional geometry is constructed and how the solid angle is actually evaluated for a given system. okay.